into what the observable signatures of TZOs are. And there are huge numbers of open questions about TZOs. We'd love to know what their progenitors are. If it is a red supergiant with a neutron star companion before they merge, then these should look like high-mass X-ray binaries, maybe. Or ultraluminous X-ray sources, maybe. Since the outer layers of red supergiants are so diffuse, it's a little hard to put our finger on what the X-ray signature of them should be. We'd also like to know about other observable signatures. Abundances are fun, but you can always throw other random ideas for how to pollute a star, for how to explain a few odd abundances here and there. So we need more. It would be great to have some IR signatures, since so much of our future capabilities are going to be in the IR. We're looking at the light curves of these objects and how they differ from normal red supergiants. We're having a lot of fun imagining gravitational wave signatures, either during their formation or during the spin down of the neutron star once it gets to the center of the star. We'd also like to know how many there are, what their lifetimes are. Is there metallicity dependence on how many TZOs there are or how they can form? Are there limits to how many we should expect to find in a population? And we'd like to know what dictates the lifetime, whether it's the neutron star becoming a black hole versus the star puffing itself apart. That gets into what the terminal product of these should be. One idea is that the star is very strongly mass losing and it eventually puffs away all of the outer material and leaves behind this sort of naked neutron star that's been severely braked and slowed down by its life inside the star. There's a paper where somebody thinks they found a weirdly slowly rotating neutron star that might be post-TZO. It's also possible these things could make supernovae, that they could just directly collapse to a black hole and disappear. If you've made a TZO, it makes it harder to make a compact binary population out of this because they have merged before this star has also made a neutron star. So it also has implications for how many neutron star binaries we might expect to see. So I showed this slide at the beginning, who cares about red supergiants? I want to justify a few of the items on here with a few quick looks at applications of red supergiants. I've already mentioned gravitational waves. Colliding neutron stars have almost certainly evolved from red supergiants that are in binaries. Their progenitors had to be between 10 to 40-ish solar masses, probably even lower than that, when they were on the main sequence. So we know that barring some early binary interaction, those stars will become red supergiants. So the more we know about red supergiant mass loss, the binary fraction of these stars, and what effect this has on their core collapse, these are all key ingredients to understanding the neutron stars that eventually wind up in compact object binaries. They're also really interesting supernova progenitors. These are by far the best identified supernova progenitors in pre-explosion imaging. So when you're very lucky, after a supernova happens, you can go back to Hubble data and maybe get a color image with more than one filter. And you can identify a star that was there and red supergiant-ish in the pre-supernova imaging that is then gone in post-supernova imaging. We really need to understand red supergiant evolution if we want to interpret those data points. So the data points you see on the right-hand side of this HR diagram in gray are the best classified progenitor observations that we currently have. So based on photometry, we've estimated a temperature, we've estimated a luminosity. These are, I think, very optimistic error bars on those parameters. These are all the different evolutionary tracks that I talked about. So single non-rotating stars, rotating stars, and the dashed line binaries, and the dotted line. So you can imagine taking one of these data points, looking at its error bars, and then trying to imply, say, the mass of that star. Usually we can't do much better when you consider all the potential error sources than somewhere between 12 and 20 masses. And we'd really like to have better mass estimates for supernova progenitors than that. So knowing how our supergiants behave and trying to eliminate or tighten down some of those evolutionary tracks are key to interpreting them as progenitors. And then finally, we know that red supergiants can be really strange and variable stars. The spectra on the left are all from the same red supergiant. This is a red supergiant in the Small Magellanic Cloud, as observed in 2004, 2005, 2010, and 2013. This star was changing its apparent spectral type on a timescale of, it turned out to be months. When it got colder, it got brighter, it got dustier, it got more luminous. It went into that region of the HR diagram where stars cannot remain stable. I think it's obvious that the star isn't behaving in a very stable manner. And we still don't have a clear explanation for what it's doing. Red supergiants will undergo photometric and spectroscopic variability like this. The variability can come from those large surface convection regions. They can come from radial pulsations in the stars. sporadic mass loss, the changes in their circumstellar dust, things that the binary companions could be doing, or mechanisms that we just have no idea about. Another aspect of Trevor's thesis is looking at evolved massive stars in TESS. The high cadence observations that we could get could be the best hope that we have of pulling information photometrically out of red supergiants, or in this case, yellow supergiants. You can see the interesting photometric differences between 3 galactic yellow supergiants that we studied. So this could give us a way to start pinning down what variability is telling us in red supergiants, but we need much more data. We have more targets scheduled in test cycle 2, and long-term observations with things like LSST, all of these programs that we think of as transient tools, will also wind up giving us really gorgeous light curves for variable stars. So I want to close with looking at what's next for red supergiants and a couple projects that we're doing to prepare for what we'll be observing with red supergiants in the next 10 years. So our upcoming space telescopes are going to be very heavily focused on IR observations. We have James Webb in March of 2021 and WFIRST for some time. They look cool. So both of these are going to be great tools for studying massive stars, period, and cold massive stars in particular. So we can study local and extragalactic red supergiants. A great tool for this is doing something like imaging pre-supernova supernova progenitors, especially with something with a wide field of view. If we can better map the observations to physical properties, this can hopefully fix or kind of scrunch down the error bars that we're putting on progenitor observations. And one great example of this is the red supergiant population in NGC 6946. So this is the supernova factory galaxy. It's had 11 core collapse red supergiant events in 100 years, 10 supernovae and 1 red supergiant that looks to have just winked out and vanished. It seems like an excellent galaxy to start surveying the massive stars as closely as we can and trying to understand the star formation history of the galaxy, how metallicity and ionization parameter and all these other things are combining to influence star formation and the birth of these progenitors. So this is a project that I've been doing with Locke. We're working on mapping metallicity across the face of the entire galaxy, mapping H-alpha as a proxy for star formation, and mapping the velocity of this galaxy, because this is a bit of a point of contention in terms of how far away this galaxy is and its dynamics. All of this will basically give us a starting map and guide to studying massive stars in the galaxy. We also recently got 42 prime Hubble orbits and parallel orbits also pointed at NGC 6946 to try and get the O and B star populations in cycle 27. So these are WFC3 and ACS images. They focus on the very bluest end of things and try to go as deep as we can. So we're hopefully going to get an O star census, and we're going to try to squeak in as many B star and cooler stars as we can. What would be amazing is to then take James Webb, or ideally WFIRST, just because of the wider field of view, and study all of these red supergiants in detail. The catch there is that to get better error bars on where we put them on the HR diagram, to get an understanding of their mass loss and dust production, we really need to start studying red supergiants in the IR. This is the optical spectrum of a red supergiant. That's the near IR spectrum. It is just as bright. They peak in their SEDs right at the break between what we start to call optical versus near IR, but they're weirdly understudied in the IR regime. So we can improve this, and we should ideally improve this before something like James Webb or WFIRST start operating, by trying to pick out the bands that are going to be the most useful for studying red supergiant populations and pulling out things like effective temperature. So this was a project that I recently did. I took a bunch of theoretical red supergiant spectra, so these are near IR model red supergiant spectra from the Phoenix models. I took some actual observed red supergiant spectra, so these are IRTF observations of galactic red supergiants, and they actually go all the way out to 5 microns. For this I was working in the near IR. And I took all of the James Webb near-CAN filter transmission throughput curves. By mashing all of these together, you can simulate what photometry of red supergiants is going to look like with James Webb. From there, you can take something like, say, a 070W minus 200W filter color, which is the red line here, and see how color maps with effective temperature. And that filter combination, unsurprisingly, is a pretty good gauge of effective temperature. You're sampling the bluest side of the star that you can get and the reddest side of the star that you can get. You're getting a good sense of the shape of the SED in the near IR. And you could probably take observations with James Webb of extragalactic red supergiants in those two filters and get a decent bead on their colors. I did this paper about a year ago. Over this past summer, a student has been working with me at UW, Megan Kokoris, on taking this exact same approach and applying it to the W1st filters. So in W1st, the best tool, unsurprisingly, is similar to what we saw for James Webb. We now have 062 minus 184 in yellow right here, which winds up as the best color to temperature gauge. There's also a lot more that you can do with color filters if you're careful. The 090W James Webb filter actually winds up being great if you want to add a third filter and distinguish between something like foreground dwarfs and background red supergiants. The red triangles here are red supergiants. The X's and crosses are regular metallicity and low metallicity dwarfs. And we're plotting 70 minus 90 on the x-axis and 90 minus 200 on the y-axis. You can see that those colors are probing a surface gravity effect in these stars that pop the supergiants out as compared to the dwarfs. What you're actually getting is a local H- opacity minimum right in the region where different surface gravity effects on the lines are going to depress the dwarf colors relative to the red supergiants. 090W also turns out to be the best filter for estimating luminosities of red supergiants from James Webb because it sits right at the peak of the SED, so the bolometric correction is going to be as small as possible. So this is all great, but red supergiants are interesting throughout the IR, and James Webb is going to be observing both near